Hello everyone, my name is Carrie Yip, and this is my presentation on trepanning, which is a manufacturing process. How trepanning works. Here we can see the textbook definition of trepanning, which is the cutting tool produces a hole by removing a disc-shaped piece core, usually from flat plates. A hole is thus produced without reducing all of the material chips, as is the case in drilling. In more simple terms, in order to make a hole, we can just move a cutting tool in a circle until it cuts all the way through. So there are two techniques pictured below. One where there are multiple cutting tools that will rotate, the other where there is one cutting tool rotating by itself. Now we can see a more sophisticated and realistic setup for trepanning. The workpiece will be rotated about an axis, and the cutting tools will also be rotating about the same axis, which is in red in this diagram. This will lead to a hollowed out workpiece and a metal core. On the bottom right, there's a picture of the before and after of the material. In the case of the research done on titanium, a trepanning process can create a hole of 165 millimeters in diameter and 2,000 millimeters in length in titanium. This same configuration led to around 82% of material utilization. So here we have a video. So here's their end result. There's the middle core and the outside, which is what we want. Okay, so things to consider when thinking about trepanning. The parameters include cut speed, feed rate, cut equivalent, and guiding hole dimensions. It is important to control these parameters before starting the process. The materials being cut are commonly metal or metal alloy. It is considered to be more economical since we're able to keep the middle part or the core to be used for other purposes. To examine the challenges, we must look at what our goal is. For trepanning, it is necessary to control the dimensional accuracy, surface roughness, straightness, and coaxiality. So on the bottom here for the research paper, we have that they reached IT10, which is the tolerance grade. Their surface roughness was around 6.3 micrometers for RA. Straightness is half a millimeter, and coaxiality was 0.2 millimeters. And so addressing these challenges, you have to control basically the chips or the axial cutting force. And so we have the cutting speed, V, and feed rate, F. And so in A, we have chips that will cause jamming and could damage the tool. Chips in B from large vibrations, which will also harm the tool. Chips in C, which could wrap themselves around the drilling rod and leads to more chip jamming. D, which is better, but it's just long for chips. And E is the same as D, as you see for the cutting speed and feed rate, except they cut the chips, so this is more ideal. This is what we're looking for when we're trepanning. And so for axial force, you want to keep it between 724 to 1,093 newtons for titanium in order to meet the dimensional accuracy and service quality requirements. And here are the references.